Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry Chapter 3. Okay, if you remember in Part 5 we were going over a phase change problem and we had to decide which absorbed more heat. Where was our Q higher? When the ice was warming up from negative 25 degrees Celsius to 0 or melting? And so then we solved for the heat equation, Q equals mCp delta T, and we found out it only takes 50 joules to warm 1 gram of ice from negative 25 to 0 degrees. And then we used the heat of fusion equation, Q equals m delta HF, to figure out it took 335 joules of energy to melt that 1 gram of ice, which is not very big. So if you think about why we use ice in drinks to cool them off, because it takes so much energy to melt ice that energy, that heat, is being taken from your drink and makes it cold. And that's why ice is so effective at cooling things. Okay, so looking at how the book solved it, they did those two equations just like we did. And they found out 50 joules it takes to heat it up to 0 degrees. And then, let's see, where did we get? 335 joules to melt it, and it takes a lot more to melt it, just like we found. All right, please write this down. Evaporation is the phase change between a liquid to a gas at a temperature below the boiling point. So when it's at the boiling point, we call that boiling, but then evaporation is also liquid to gas, but it happens at lower temperatures. So what happens? How can you boil water when it's not hot enough to boil? Well, you're evaporating it. So a molecule is going to Now, molecules are always moving around, and sometimes a molecule hits a surface molecule and gives it enough energy that that molecule goes into the water vapor stage. So on average, not all the molecules have enough energy to be gas, but one can be higher than average and leave. Condensation is the opposite. It is a phase change from gas to liquid at temperatures below the boiling point. So, what's going on here? So you're going from, like, let's say water vapor in the air is maybe condensing on a cold can of pop, and that is happening at a temperature well below what the boiling point is, and that's when that water vapor molecule in the air hit that cold pop can, and it gave all of its energy to the pop can, and it lost so much that now it's just liquid and it doesn't have enough energy to be zipping around like a water vapor. It is a liquid water droplet now. Okay, so the heat energy given off during condensation is called latent heat. So kind of like heat that is laying around, stored heat. And we know that water has a very high specific heat. So when water vapor condenses to water droplets, like in the atmosphere in a cloud, and you times that by 1,000,000, billion, gazillion, that's a lot of energy being given off. And that is what creates all that energy for the weather that we have and like the storms that we have. A lot of times you'll have big masses of air, like cold and warm, hitting each other in the spring, and then we get these violent thunderstorms. And that's because of chemistry and water's high specific heat. This also, latent heat, is what drives climate. Kind of like, why is Seattle north of us, but it hardly ever snows there and has summer temperatures usually around in the 70s, whereas ours are 90 degrees and, well below freezing for winter. Well, it has to do with the moderation of temperatures because of the Pacific Ocean, and all the other climate and weather things have to do with a lot with water. Okay, so coming down to this other thing, condensation and evaporation, well, that's responsible for the water cycle, and you should have learned about that in elementary school. Okay, looking at this picture, we have water, and then we have some condensation in that bottle. And so these water droplets, all these little water molecules, are representing the water here, and then some of these bump the surface one and give it lots of energy, and then it goes and becomes water vapor, which then condenses back into liquid water when it hits the side. But it was water vapor for a short period of time. It was flying free. Okay, so let's talk about pressure and altitude. So I have a friend who lives in Denver, Colorado, and water boils there at 95 degrees Celsius instead of 100 degrees Celsius. Why? Is Denver a freak place? No, it is has to do with chemistry. So we know that Denver is a mile high. It's about 5,000 feet above sea level. And if you have a higher altitude, you have a lower atmospheric pressure. And that's actually just because there's less air pushing down because you're higher up, so there's less air. And that pressure is going to affect phase changes like boiling. So let's look at our graph here. Please write this down. Phase equilibrium diagram. This shows the temperature, pressure, and phase change. And then we're going to make a simplified view of this diagram in your notes. So you should have pressure on the y-axis and temperature on the x-axis. And then this nice curve between gas and solid here, and gas and liquid here. And then you have a line going up between the solid and the liquid phase. So let's talk about how to read this. So at 0 degrees Celsius, so you should label that temperature, at normal pressure, which would be right about here, normal atmospheric pressure, you have the freezing or melting point, depending on which way you're going, of water. And so we say that's A. So if you lower the pressure, doesn't change it a whole ton, but it does over here when you're liquid and gas. Okay, and so then you can see that here is the curve between the liquid and the gas phase. And so at normal atmospheric pressure, 100 degrees Celsius is right where it boils. So please label the boiling point and make sure you have gas, liquid, and solid labeled as well. And if you notice, if you go to Denver, it has just a little bit less air pressure. So the boiling point is going to be just a little bit less. And let's talk a little bit about what this means. If I have less pressure, you can see I could actually have water that is solid, liquid, and gas at 0 degrees Celsius. So that's called a triple point. Or if I have, I could go right from the solid to the liquid phase. If I had it under very low pressure, I could go right from ice to water vapor at a very low pressure. Okay, so we talked about that triple point. Please write that down. The temperature and pressure where gas, liquid, and solid are all in equilibrium. And it's right there. All right, so let's talk about how it affects us, temperature, pressure, and phase changes in our lives. Okay, so they affect the weather, they affect how comfortable or uncomfortable it feels, and they affect if it's going to rain, snow. So these things, temperature, pressure, and phase changes, actually affect our daily life a lot. So it depends on what you're doing. Can you have a game that day? Do you feel gross and sticky and hot, or do you feel like is your skin all dry? Or do you feel, is it just like a perfect temperature and humidity? So please write this down. Relative humidity is how much water vapor is in the air compared to how much that air can hold, and it depends on the temperature. So we know that warmer air can hold more water, more water vapor than cooler air. So if you have the same amount of water at a higher temperature, it will feel drier than if it's at a colder temperature. So really comfortable is about 50 to 60%. And the temperature at which the air is saturated and it is holding all the water vapor it can hold is called the dew point, and it changes depending on the temperature. Okay, so taking a look at this pressure versus temperature graph, we can see if we hold the pressure constant, as we increase the temperature, it can hold more liquid. So right here, the water vapor at this pressure would be saturated, but here it would not be saturated. And so when it's saturated, when it can hold all the water vapor it can at that temperature, it's called the dew point, and its relative humidity would be 100%. So if you have the same amount of water vapor at 20 degrees, you'd be 100%. But if you had that same amount at 30, you would not be at 100%, and the air would feel drier. Okay, so let's talk about dew. So when you have warm temperatures in the day, so let's say it's like here, and then it's going to cool down at night, and then that water vapor can't stay in the air. There's just too much water vapor in the air for that temperature. So it's going to condense on leaves and blades of grass and stuff, and that's why when you wake up in the morning there is dew. Okay, let's look at the chemistry connections at the end of chapter 3. So you should have read these 2 pages, and we're going to discuss this. So this is refrigeration by evaporation. So please write that down, and we're going to discuss it in class. Water from the moist pot, so they have a pot within a pot, and the water from the moist pot is going to evaporate, and we know that water has a high specific heat, so when water evaporates, it takes energy with it, it takes heat with it, and it takes heat from the food inside of the second pot. And then when you're cooling things down, they don't spoil as fast. So I feel like that's a pretty ingenious way of having refrigeration without any electricity. So what? Well, this could be a game changer for people. So people could make more money by selling their vegetables, and then they could buy the needed supplies. Like maybe they can make enough money that their kids could go to school, or maybe they could make enough money that they can afford the doctor. And so this could be a real game changer for a lot of people. And our chapter 3 notes are finished. All right, good job, everybody.